All right, let's go ahead and open up to page 45. We're going to start our next section today, 1.3, and it's a continuation of the function values and notations that we've been talking about, but we're really going to dive deeper into graphs in this section and future ones. We're going to start taking a look at graphical characteristics, how we can look at a graph and think about certain properties. Like when's the graph positive, when's it negative, when's it increasing, when's it decreasing. We can maybe identify different function values. Maybe we can start to combine function values together, like look at multiple points and manipulate those values. So a lot of different things with graphs that we're going to get to today and in the future. So on page 45, we have this graph at the top, and for each of the following function values in the table, we're going to utilize f of x, which is the dashed line. So I don't know if this helps or not, but maybe you want to label which one's which. F of x is the dashed line, and g of x is the solid line. All right, so we can keep those straight. Now, yesterday and previously this year, kind of as review, we've been going over function notation. And yesterday we were going over how whatever's inside the parentheses, that's typically representing an input value, which is usually an X amount. And then if you input something, that means you output something. In this case, our output or answer would have been 2. So that represents a Y value. So if you know an X and you know Y, you can write it as an ordered pair if you choose to. So using these two graphs, we're just going to go through a bunch of different function value notations or questions, and we're going to try to pick apart what this graph is telling us. So if we take a look at the first one, f of negative 1, notice how it's inside the parentheses, so that's representing an x value. We're going to go to the spot of negative 1 on the x-axis, and using the f graph, which is the dotted one, we're going to see what the output would be. Okay, what the Y value is. I know the numbers might be a little grainy or fuzzy on your paper. Sometimes counting might be better. Is that 6? Looks like it. Okay, so we input negative 1, we output 6. Now yesterday we did kind of the same thing, but we had equations to actually check our work. Remember we did the absolute value and the square root. We don't have an equation for this f of x graph, so we can't really check our work in this case. Okay, we just have to make sure that we're confident and comfortable with our answer. Do you guys think you can try the next 1, 2, 3, 4, 5?
Yeah.
Yeah? Do it. Some of them are tricky. So I ate a mint this morning, and there's like a little chunk lodged in my throat, and I can't get it up and I can't get it down. I don't know if you've ever felt that before. Like it's just in limbo. Ice sometimes, yeah. That melts faster.
Yeah.
So this is kind of uncomfortable, but it's getting there.
We're just doing our job. Do we have any?
Good morning.
Thank
Thank
you.
you.
Oh, we got one more. No thanks. Happy Friday.
Yep. All right, let's check them out. If you were to input -9 into the f function, okay, that's the dotted one, what would you get out? Yeah. No solution. All right, so -9 happens to be right here. If you do trace it up, you get the open circle, but that's signifying that there's no actual point value there. So you can write no solution, does not exist, undefined, okay, anything like that. So it kind of looks like there's a graph there, but since it's an open circle, that means there's nothing there. What about if you were to plug in 5? -5 sound good? Is that okay, Sam? Let's see. Oh, I think you used a solid graph. Okay, so you found the G value. So plug in 5, get out -5. All right, so now we're switching over to G, which is the solid graph. If you were to plug in -3.2, this one's a little, maybe, let's check it out. -3, and then 0.2, we're a little bit in. So we're not exactly 2, we're just like slightly under it. So 1.8, 1.9, 1.7, okay, I guess. Like I said, some of these might be a little tricky. What about G of -11? Looking at that solid graph, what do you think, Pedro? -2. All right, so G of -11. Go to the solid graph. We have a closed circle. That means we can include that value, and the Y output's -2. Good. G of 7 looks like -1. How do we do? Good? Okay, so notice how those were individual function values. You input something, you get out something. The next few we're going to take a look at are a little bit more involved. That doesn't mean difficult, okay, just a little bit more involved. And it's the notation that we have to get used to. Okay, ask ourselves, what do we think this is asking us to do or asking us to find? So if you take a look at the first one, we want to take f plus g and somehow use this number 3. Can we kind of brainstorm what we might think this is asking us to do? What do you think, Peter?
F of 3 plus G of 3.
Okay, so very similar to this -1, -9, and 5, this 3 is representing an input value. Okay, this is an X number. And we specifically want to input that 3 into the f and g function. So we're going to get two separate answers, like if we plug into f and plug into g. And according to the notation, we want to take those two separate answers and add them together. Okay, so we're basically finding individual values, but we're going to start combining our answers together. So f of 3, I have so many dots on this graph, let's erase them. So f of 3 is the dotted one. Looks like we would get -6. G of 3 is the solid graph. Looks like we would get +6. And the notation is asking us to add those together. So -6 plus +6, we get 0. Again, half the battle sometimes in math is just understanding what the heck we need to do. Okay, what does it mean? What's it asking us to do? So take a look at the next one. Very similar notation. Okay, -3 is an X input amount, and according to the way it looks, we want to find the F answer, the G answer, and then subtract them together. So X location of -3. The Y value for F looks like 6. The G value looks like 2. And we want to subtract those results, so we get 4. Okay, you guys try the next one. Let's see, if you input 9 into G, you get -3. If you input 9 into F, you also get -3. And we want to subtract those. Notice how that would change to a plus. So -3 plus 3, 0. All right, good. All right, so let's go ahead and try some more kind of amped up ones. Notice how this time we're bringing in some multiplication or perhaps division, but we still got to take a look at the notation, ask ourselves what is it asking us or representing or telling us to do. So we want to take, in this case, 2 times the answer that we would get from the F graph if we were to substitute in -4. So 1, 2, -4. F graph is the dotted one. Looks like we would get 6. And then we want to subtract the answer we would get from the G graph if we were to plug in -6. Which looks like -2. Okay. So we have a 12, and then a plus 2. We have that negative. Looks like we get 14. Okay. Let's keep going. So G of -8 looks like -2. F of 0 is 3. According to the notation, we want to add those together, but then we also have to divide by G of 0, which looks like 4. So we're left with 1/4. We're doing okay? All right, let's keep moving. So next notation, we got to take -2 times the answer we would get from the G graph if we were to plug in 8. So 4, 5, 6, 7. There's 8. Solid graph has a y value of -2. We then have to subtract 3 times the answer from the F graph if we were to plug in 17. So F is the dotted line. Let's see. 7, 8, 9, 10, 11, 12. We only go to 13. It's asking us for 17. What do you want to do? Quit? No. No. Yeah?
Figure out the slope of the line.
Okay. We can take a look at the line a little further. Right. Take a look. The line has an arrow on it, right? It's not an open circle or a closed circle, meaning it just ends there. If you have a line or if you have an arrow, it's going to continue. So we should be able to eventually figure out if we were to plug in 17, what would we get? And the only way we can do that, since the graph doesn't go out that far, is to figure out the equation of the line, or perhaps use the slope to help us do that. So the equation of a line, if we can figure out the slope and the y-intercept, we should be golden. Okay, y equals mx plus b. So let's try to find 2 really good, easy points on that line to calculate the slope. I don't care which 2 you pick. We just got to find rise over run. What does it look like the slope might be? Again, I know it's kind of grainy, but try to find good ones. Yeah.
1.
I would agree. 1/2 kind of looks good. So there's a good point. There's a good point. Up 1 over 2. Okay. So there's our slope. Now we got to figure out what the y-intercept would be. So if we were to extend the line backwards, kind of where would it cross the y-axis? So if we use the slope to our advantage, down 1, let's see, down 1 over 2, we would be here. And if we went down 1 over 2, we would be somewhere on the other side of the y-axis. So we got to cross somewhere. 1, 2, 3, 4, 5, 6, 7. Kind of looks like 7.5. It's not going to be a nice, well, I don't want to say nice. Every number is nice. It's not going to be a whole number. Okay, so -7.5. So we got to ask ourselves now, if we were to plug in 17, what would we get? So half of 17 is 8.5, okay? And if we subtract 7.5, we're left with 1, okay? So even though we couldn't get that result from the graph, maybe we could use the graph to help us write an equation to help us out. Okay, a little thinker there. So if we keep going, we have negative 2 times negative 2, which is 4, minus 3, so we're left with 1. How are we doing with function notation so far? In a graph? Pretty good. All right, so we're going to switch it up a little bit now. Take a look at the next few. Notice how the notation, the way it looks, is a little different. So find the values of x. Okay, previously all of these inputs we had, or numbers, represented x values. So now they want us to find x, which means what does this negative 6 represent? If we want to find an x, then it must be a y, right? Okay, so this is a y value. So let's go ahead on the y-axis to the value of negative 6. So that's right here. And we got to ask ourselves, when does the dotted graph, because that's the f of x graph, kind of touch that negative 6 horizontal line? Looks like right there. And that point has an x value of 3. All right, let's try the next one. Very similar notation, okay, but this time we have a negative 3. So let's find the y value of negative 3. And we got to ask ourselves, when does the f graph, so that's our dotted line, kind of cross that negative 3 value? If you look carefully, we actually have 2 spots. So we're going to have 2 answers. X equals, looks like 2, and what is that, 9? All right, the next one we have a y value of 6. So that's somewhere right there. And they're asking us about the f graph. So when does the dotted line have a y value of 6? At which x values? What do you think, Alex?
Would it be negative 6 under the 0?
Negative 6, okay, so that's right here. To where?
To 0?
I don't know if it's 0. I think it stops at negative 1. Okay, so notice how we kind of have an interval, right? We have negative 6 to negative 1 and everything in between them, right? So just like we do domain and range, like beginning point, ending point for an interval, we might have to do that here. Alex told us it begins at negative 6, it ends at negative 1, and we got to ask ourselves, can we include those endpoints, right? Don't we have a closed dot at negative 6 and at negative 1? So we would have those brackets. So you're telling me any x value, including negative 6 and negative 1 and anything in between, will have a y value of 6 in this case. Is there another one? You see it?
Well, if we continue the line from earlier, wouldn't it accumulate to the 6?
Remember that arrow? Arrow means it keeps going. Okay? Remember, graphically, you can only see so much. It depends on where they want to stop the window. But with the arrows, we got to be careful. That means it's going to go on forever. So if it continues in that path, notice how it would eventually have a y value of 6. We got to figure that out. Now, we had the equation from before, so maybe we can use that to our advantage. Okay, if we have a y value of 6, let's go ahead and add 7.5 over. So that'd be 13.5. And then you have to multiply both sides by 2 to get rid of that 1/2. So if you double 13.5, looks like we get 27. Okay, so that's actually not on the graph. We cannot physically see it, but we have to be aware or cognizant of those arrows, okay, that we might have other values. So we can have any x value on this interval, but we can also have an x value just at 27. Can you guys try the G ones? Check out the solid graph. Remember, G is the solid graph, so if we take a look at -6, the solid graph never ever touches that y value, that horizontal line, so you could have write none, no solution, undefined, doesn't exist, something like that. If we check out -3, the solid graph does touch that y value, just barely, and looks like an x value of 9. And then if we check out 4, looks like we have 2 solutions for the solid graph, 0 and 4. How'd you do? Good, Cole?
I don't really get how you got 9. Oh, there's a negative. I didn't see it. I'm not.
Oh, that one?
Yeah.
Yeah. It's okay. We do good? All right. Let's keep this train moving. Look at the bottom ones. Okay, slightly different. Again, a little bit more involved. If p of x is this quadratic function, for what values of x is this statement true? Okay, so we got to ask ourselves, what does that mean? What is that asking us to do? Take a look at the way it looks. Function notation. It's like a different language. Any ideas? Let's see. Do we know what p of x is? They told us, right? That was the equation. So maybe on this side, instead of leaving it as p of x, we'll go ahead and rewrite it as the actual equation it is. According to the function notation, okay, the way it actually looks, we then have an equal sign. And then after the equal sign, it says g of -3. Can we replace that with something? Can we figure out what g of -3 actually is? Yeah, we have the graph up top, right? So -3, g was the solid graph. Looks like we get out 2. So notice how that function notation looks a little weird. It's actually asking you to solve this equation. Okay, we took whatever p of x was, the quadratic, and we set it equal to whatever g of -3 was. Okay, this was a y value or an output. So how might we go ahead and figure out the values of x from there? I'm hoping that little power of 2 is like sending a light bulb off in our head, like maybe we can do this. Yeah. Factor. Okay. Before we factor though, what do we gotta do first? Go, Sebastian. We gotta set equal to 0. We gotta add the 2 over. Yes. Thank you. Alright, so factoring is all well and good, but if we're actually going to solve the equation by using some factors, we need it equal to 0. That way we can break them up. So if we subtract the 2 over, we get negative 15. Alright, so factoring techniques. Did these earlier this year. Is there a GCF? No. Does it fit the IAM profile? What I call IAM factoring? Yes, because the A value is 1. So let's think about two numbers that multiply to negative 15 but add to 2. Yes, ma'am? 5 and negative 3. All right, so our two solutions then, if we broke up the factors, we would get negative 5 and 3. Okay, so function notation, we're getting used to what it's asking, okay, what things represent, how we can find points on a graph, but also how we can use function notation to represent solving an equation. Let's check out the next one, kind of similar. If q of x is this absolute value function, find the values of x that make this statement true. Okay, take a look at the way it looks. They say q of x, but they also mean the absolute value. They say f of 5, but they probably mean a point on the graph. So let's go ahead up to the graph. X value of 5. Remember the f function was the dotted one. So our output would be negative 5. Can you guys go from there? Yeah, give it a shot. So if we start thinking about how we can solve for x, moving terms to the other side, isolating the variable might not be a bad idea. We can subtract the 4, divide negative 3. So we're left with this absolute value equation. But like we saw yesterday, absolute value is a V shape. Maybe we have two answers, okay, one on each side of that V. So we'll go ahead and break it up, keeping one of the equations with a positive 3 and the other one with the negative 3. So we'd get 6 or 0. How'd we do? Did we remember to break it up? Yeah, good. All right. Let's go ahead and flip to the back. So in addition to these graphs, we can start taking a look at other characteristics. So point values, function values, those are all well and good, but there are other things we can analyze about a graph. And what we're going to take a look at now is just when a graph is increasing, decreasing, or constant. I know you've done this before. Okay, increasing typically means going up, decreasing, going down, constant is flat. But what we're going to get used to doing is describing where on a graph that is occurring, okay, using interval notation, kind of math language. So if you take a look at these graphs, I know we can clearly identify where a graph is decreasing, where a graph is increasing, and when it's constant. We're going to practice writing the intervals to describe those locations. So very similar to how we did domain and range. Remember, like dragging your pencil? We're going to do that here. So when you identify those sections, we're going to start on the left, just like you read a book, left to right. We're going to start on the left and ask ourselves, when do we start to decrease? At which x value? Looks like -5. Okay, so we'll go ahead and write down -5. And as we continue to drag our pencil, we got to ask ourselves, when do we stop decreasing? That's our question at hand. Okay, we're analyzing when a graph is decreasing. Looks like we stop at -3. Now we got to ask ourselves, okay, because this is something different than domain. For domain, we ask ourselves, can we include that point? Okay, is it a closed circle? The question right now is, are we decreasing? Okay, so you got to ask yourself, if you're standing at that point right there, are you going down? If you're standing at the top of a mountain, are you going down? No. If you're standing at the bottom of a valley, are you going down? No. Okay, so if this was domain, we would use brackets because we definitely do have closed circles there, but that's not the question we're trying to answer. We're trying to answer, when are we decreasing? When are we going down? So if we're not decreasing there and we're not decreasing there, we must use parentheses. It's different than domain and range. It's a different question that needs to be answered. We identified another interval, so we're going to throw in that u. And let's drag our pencil over to the other side. It looks like that section starts at the x value of 4 and ends at the x value of 6. Okay, the question at hand is, are we decreasing at 4? Are we decreasing at 6? If you're standing right there, are you going down? No, not yet, right? You haven't started the process of going down. If you're standing right there, are you going down? No, because you stopped, right? That's an endpoint. So if the answer was no for both of those, we need those parentheses. Yes?
Will these ever come back then?
No.
So they're not going to be
They're always going to be parentheses, and that's what we're going to discuss in the next section. That's great, okay? Let's try increasing, okay, when we're going up. If you look at the x-axis, it looks like we start at -3 and we go to 0. We got to ask ourselves, are we increasing at those spots? Are you going up at -3? No, because you're at the bottom of a valley. Are you going up at 0? No, because you start to go straight afterwards. You don't continue to go up. All right, so those are parentheses. Our answer was no. Constant looks like from 0 to 4. And are we constant right here? We're starting to be, perhaps, because we go up, but if you're standing right here, you haven't really started the constant path just yet. So that would be a no. Are you constant right here? Okay, you stopped being constant, but notice how you do not continue to be constant afterwards because you start to go down. So that would be another parenthesis. So like Alex was kind of hinting at, if you take a look at all these points, notice how we have some type of change in direction. If you have a change in direction, that's causing you to change if you're going up, going down, or if you're being constant. So the moral of the story is, should your intervals be identified as closed, meaning brackets, or open using parentheses? If we take a look at all of them, they're always going to be open intervals, meaning you cannot include those endpoints. So we'll say always use parentheses. This is for increasing, decreasing, or constant. because we're changing those directions from up to down, down to up. Maybe there's a constant thrown in there. Now this is different than domain and range, which we're going to practice again at the bottom, okay? Identify the domain of the graph and the range of the graph. So domain is from left to right. Where does the graph begin? X value of -5, okay? As we drag our pencil across, we don't have any open holes that we have to be concerned about. Looks like it ends at 6. Good luck, Autumn. Okay. So since this is a domain question, we got to ask ourselves, is this X value included? Yes, because we had a closed circle, so that would be a bracket. Is this X value included? Yes, because it's a closed circle, so we need a bracket. Notice how the question is important. Yes?
They always be correct.
For this graph, yes. If this one was an open circle, that would be a parenthesis. Okay? So that, for domain and range, it's not as clear cut as it was before. Okay, you have to ask the question, and if it's yes or no, use brackets or parentheses. All right, let's try the range. So low to high, where does the graph begin in terms of the y's?
Oh wait, no, maybe 3.
That's the x, or it ends at 6, right? The y value is -3. Okay? And as we drag our pencil up, we do not have any open circles that we have to be kind of leery of. Looks like we end at 5. Okay, now this is a range question. We got to ask ourselves, this beginning point here, can we include it? Yes, because it was a closed circle. This ending point at 5, can we include it? Yes, because it was a closed circle. So notice how in this particular example, for this graph, the domain and range had brackets, but increasing, decreasing, constant had parentheses. Okay, it's all about the question that you are trying to answer. All right, we're going to try a little bit more of that tomorrow, but we're going to analyze a different graphical characteristic, like whether we're positive or negative. So we're starting to look at function values, increasing, decreasing, constant, and we'll get into some more properties, not tomorrow, I meant next week.